In this video, I will explain about the star to delta and delta to star transformations. See, if you see if the complexity of the networks goes on increasing, then we cannot just use Kirchhoff's laws, Ohm's laws, or the series parallel combination of the impedances to solve it. Okay, in that cases we can use this star delta transformations. Means if there is a possibility of converting the impedances which were corrected in star to delta or delta to star, then we can use this transformation and reduce the complexity of the network. So mainly I can say the star to delta or delta to star transformation, they are used in reducing the complexity of the network. And we also know that there are three-phase circuits, right? So in three-phase circuits, these elements, they will be connected either in the star connection or in the delta connection. Okay, so if you see the impedances or the resistors like this in the network, that means they are connected in the star form, or it will be like this. This is also star form. Or if you have, so this is also a star form. So in three-phase circuits, if the impedances are connected in this form, this is called as star connection. So it has four wires. It has four wires. This is a common point. That means the impedances are connected in such a way that one of the terminals of that, okay, one of the terminals will be connected to a common point. That is called as neutral point, or it is also called as star point. It is a neutral point or it is called as a star point. So it has four wires. The three are phase wires and one will be your neutral wire. In some cases, this neutral wire will be optional. Okay, inline voltage and phase voltage, that will be different in case of star. So it will be used for longer distances. Okay, so when I consider another one, that is nothing but the delta. See here, this is star. It is also called as Y connection. Okay, Y form. Okay, so because you can say it is similar to the English alphabet Y, right? And it is also called as T connection, star connection, Y connection, or it is also called as T connection, because we can write this in this form. That means, see, this is appearing like T, right? So this is also called as T connection. Next, when we come for this delta, the impedances are connected in such a way that the second end of the first one will be connected to the first end of the second one, and the second end of the second one will be connected to the first of the third one, and so on. That means it will be forming a closed path. So this is a closed path. So this is your delta connection. This is delta connection. And in networks, you can also see this form in this form. Okay. So this is similar to pi. Similar to pi, right? So this is also called as pi connection. This is T connection. This is pi connection. Okay, we can also see it in the networks like this. So this is all about your delta and star connection. See here, this delta, it will be having only three wires. Okay, it doesn't have any neutral or star points. Okay, that is in delta. It has only three phase wires. Inline and in phase voltage, that will be same. And hence what happens, it requires more insulation, not like your star. Star, it has four wires. One is neutral, three are phase wires. Inline and in phase voltage, they will be different. Okay, and therefore the insulation required for this star connection, it is less than that of the delta. So it is used for the longer distances. This is used for the shorter distances because it needs more insulation. Okay, because of your inline and in phase voltage is equal. Okay, so this is all about the delta and the star connection. So let us see star to delta transformation. or we'll start with delta to star. Okay, we'll start with delta to star. Delta to star connection. So now I will consider delta connection first. Okay, so this is your terminal 1, this is the terminal 2, this is the terminal 3. Okay, so this is ZA, this is ZB, this is ZC, and I have to convert this delta to star. Okay, so what I will do, I will write that star inside this, so it has a neutral point. This is Z1, this is Z2, and this is Z3. Okay, so the delta connection is outside, and inside delta I have written the star connection. So let us convert delta to star now. Okay, so first I will consider the terminals 1 and 2. Okay, terminals 1 and 2. Okay, in the delta I can replace this. Okay, see 1 and 2, if I consider like this, in between 1 and 2 we have ZB, right? So ZB. So third point, it is common to both 1 and 2. I'll consider that here. Okay. So 1 to 3. This is 3, right? So 1 to 3 you have ZA. You have ZA. And here 2 to 3 you have ZC. Okay. I can write like this, right? I am just converting this to this form. I am considering 1 and 2 terminals. Now I am considering the 1 and 2, not 1 and 3, just 1 and 2. Similarly, I can write for 1 and 3. See, 1 and 3, in between that we have ZA. I will take this point 2 here, which is common to both 1 and 3. Okay, so in between 1 and 2, we have ZB. And here we have ZC. Okay, likewise, we will consider 2, 3 terminals. In between 2, 3 you have ZC. And here this is the point 1. So in between 1 and 2 you have ZB. And here you have ZA. Okay. So what will be your impedance here in Z12? Z12 will be the impedance if I see from here. If it is seen from here, it is Z13, and if I see from here, it will be Z23. That will be the impedances. So you know ZA and ZC, they are in series. So I can write this as ZA plus ZC, right? This is ZB plus ZC because they are in series. ZA plus ZB. So now we can see that ZB is in parallel with this series combination. So what I can write, Z12 that is equal to ZB parallel to ZA plus ZC. So you know when two impedances are in parallel, we can write that as Z1 into Z2 divided by Z1 plus Z2. So here Z1 is your ZB into ZA plus ZC divided by ZA plus ZB plus ZC. This is your Z12. Then what is your Z13? It is ZA in parallel with ZB plus ZC. So ZA into ZB plus ZC divided by ZA plus ZB plus ZC. Next we have Z23. Z23 is ZC in parallel with ZA plus ZB. So ZC into ZB plus ZA divided by ZA plus ZB plus ZC. So now we have found out the impedances between these terminals. See, in between the 1 to 2 terminal, now we will go for the star connection. So delta, we have found out the equivalent impedances now. Okay, so now let us consider the star connection. So in between 1 and 2, you have 2 resistors in series. Only you consider these two. So that is Z1 and Z2. So that will be your Z1 plus Z2, right? That is in star combination. It is Z1 plus Z2. So that is your Z12. I'm considering star now. Next we have Z13. In between Z1 and Z3, star combination, it will be Z1 plus Z3. Next Z23, it will be Z2 plus Z3. Now I can equate these two, that is from star to delta. So Z12 is Z1 plus Z2, that is equal to, what is the value here? It is ZA, ZB plus ZB, ZC divided by ZA plus ZB plus ZC. Then here Z1 plus Z3, that is equal to ZA, ZB plus ZA, ZC divided by ZA plus ZB plus ZC. Okay. Then we have Z23. We have Z23, that is equal to Z2 plus Z3, that is equal to ZC, ZB plus ZC, ZA divided by ZA plus ZB plus ZC. Okay, so we have got these three equations here now, 1, 2 and 3. From this we can derive Z1, Z2 and Z3. Okay, how? We will see it now. See Z1, I can find from this Z1 and Z2 and Z3, okay, what if I minus like 2 minus 3, what if I do like this? We will get Z1 plus Z3 minus Z2 minus Z3, so Z3 minus Z3 cancels, so we will remain with the Z1 minus Z2. Z1 minus Z2, that will be equal to, see the now right side, ZA ZB, ZA ZB plus ZA ZC minus ZB ZC minus ZA ZC divided by ZA plus ZB plus ZC, which is common now. So these two gets cancelled. So Z1 minus Z2, that is equal to ZA ZB minus ZB ZC divided by ZA plus ZB plus ZC. So you know Z1 plus Z2 here. So I will write it here. ZA ZB plus ZB plus ZC divided by ZA plus ZB plus ZC. Now if I add these two, this gets cancelled out. So remaining is 2Z1. See here in this ZB plus ZB ZC and ZB ZC, these are opposite signs. So these two gets cancelled out. So it is 2ZA ZB divided by ZA plus ZB plus ZC. Okay, so 2 gets cancelled out. So remaining is Z1, that is equal to ZA ZB divided by ZA plus ZB plus ZC. So this is from the delta connection and this is star connection. So we can find out Z1 using ZA ZB ZC. How? See, Z1 is opposite of these two, okay, like this, ZA ZB divided by all the impedances sum. That is what we can write like this. So simplifying, next we can find out Z2, Z3 in this similar manner. Okay, we will get Z2 as, use the same method and find out Z2 and Z3. Okay, so Z2 will be, see the opposite one. What is opposite one? That is ZB ZC divided by sum of all the impedances. So ZA plus ZB plus ZC. Then what will be your Z3? What will be your Z3? Opposite one like this. Okay, adjacent ones. So we can write it as ZA, ZC divided by ZA plus ZB plus ZC. So this is how we will convert delta to star or delta to Y transformation. Now we have to convert star to delta. Okay, now all the impedances from the star will be known. We have to convert it into delta. How we are going to convert it? Using this, we will convert. Okay. What I will do is, I will multiply these two. Z1, Z2, that is equal to ZA, ZB square, ZC divided by ZA plus ZB plus ZC whole square. Okay, then I will multiply these two, Z1, Z3, that is equal to, okay, ZA square ZB ZC divided by ZA plus ZB plus ZC whole square. Next is Z2, Z3, ZA, ZB, ZC whole square divided by ZA plus ZB plus ZC whole square. Okay, so this is what we have got. Now what we can do is, I will add all this. Okay, I will add all this. Z1, Z2 plus Z1, Z3 plus Z2, Z3. What you will get? See here, it is ZA, ZB, ZC. I will take ZA square, ZB, ZC, ZA, ZB, ZC square divided by ZA plus ZB plus ZC whole square. Okay, so we can also write this is ZA, ZB, ZC. I can take it as common. Now we are left with ZB, here ZA, and here it is ZC. ZA plus ZB plus ZC whole square. So this and this gets cancelled. So we have only ZA, ZB, ZC divided by ZA plus ZB plus ZC. That will be your this equation. Okay, so this is equal to this. Now from this, okay, you know ZA, ZB divided by ZA plus ZB plus ZC is Z1. Okay, this is your Z1. Okay, so this can be written as Z1 ZC, right? Z1 into ZC. Now we have to find ZC. We have to find the delta parameters, right? So delta C, ZC we have to find. So ZC is equal to, if I bring Z1 to the denominator, so divided by Z1, so Z1 cancels out, so left with Z2. Here if I divide by Z1, you will be left with Z3. Then here if you divide by Z1, it is Z2, Z3 divided by Z1. So this is your ZC. Okay, so similarly, what happens? You are having ZA, ZB, ZC divided by ZA plus ZB plus ZC. This is what? This was the sum of these three, right? So in now we substituted this as Z1. But what I will do? I will replace ZB, ZC by ZA plus ZBC by Z2. Okay, if I replace by this, we will get ZA, Z2. So if Z2 comes in denominator, you will get another equation, that is ZA is equal to Z1 plus Z3 plus Z1 Z3 divided by Z2. Okay. Now if I substitute ZA ZC, leaving out ZB, if I substitute ZA ZC, this one as Z3, we will get the value of ZB. ZB is equal to Z1 plus Z2 plus Z1 Z2 divided by Z3. Okay, so this is the value of ZB. So we got the value of ZA, ZB, and this is ZC. See, if you want to find out this value, okay, without deriving this in problems, you cannot sit and derive the whole thing, right? So see, ZA, you have to find ZA, means opposite to this you have two impedances. So sum it, Z1 plus Z3. Then whatever you have summed, in next term you take the product of that, that is Z1 Z3, and another remaining impedance will be there. No, you have to divide it. So see here, ZA is equal to Z1 plus Z3 plus Z1 Z3, product of this divided by Z2. If you want to find the ZB, then opposite ones, that is Z1 and Z2. Okay, Z1 and Z2, first sum it, then product divided by the opposite impedance, the remaining impedance. If you want to find ZC, take these two opposite impedances, sum it, then the sum of the products of these two, then divided by the remaining impedance. This is how we are going to convert star to delta. See, we have to find the equivalent resistance that is between the two terminals A and B. So we are given with this network. Okay, see here, we have a delta configuration here, and outside also we have a delta configuration. So I have to find the equivalent resistance between these two terminals. So what I can do is, this inside delta I can convert it into star configuration. So this is your delta, right? That is, each resistance is of value 2 ohm. See, when you are converting from delta to star, if all the resistances are equal, then equivalent star, it will be having the value R divided by 3. Each resistance will be divided by 3. But when you are converting from star to delta, then the delta resistance, that each resistance will be multiplied by 3. Okay. So now, since we are converting this delta to star, so inside I will write a star diagram now. What will be the value? It will be divided by 3 because we are converting from delta to star. So this value will be 2 by 3, this will be 2 by 3, and this will be 2 by 3. Okay, so now I can draw this. Okay, so first it is delta, and inside we have 4 ohm, this is also 4 ohm, and then we have 4 ohm. This delta is converted to star, so that star configuration I will write like this. This is the star point, yes. So this is your 4 ohm, this is 2 by 3 ohm. This is 2 by 3 ohm, and this is 4 ohm. 4 ohm, 2 by 3 ohm. This will be 2 ohm, 2 ohm, and 2 ohm. So inside you can see this 4 and 2 by 3, that is in series. Here also 4 and 2 by 3 is in series. 4 and 2 by 3 is in series. That means 4 plus 2 by 3, that will be equal to 14 divided by 3 ohms. So now I can redraw it once again. So this is 14 by 3, this is 14 by 3, this is also 14 by 3. So outside you have the delta configuration. Okay, so this is 2, this is 2, this is 2. So these are the terminals A and B. Now what I can do is, to find this equivalent resistance between A and B, I can convert this star to delta once again. So you know, once again they have equal values, that is 14 by 3. So whenever you are converting from star to delta, the resistance value will be multiplied by 3 when all the resistances are equal. So 14 by 3 into 3, that will be 14 ohms. So you have 2 ohms here, 2 ohms and 2 ohms here. So inside we will have another delta configuration. Okay, we have delta configuration because I have converted this star to delta once again. What is the value? It is 14 ohms because 14 by 3 into 3. Now I have to find in between these two. So we know that these two resistors are in parallel, these two are in parallel, these two are in parallel. Parallel means it is R1 R2 divided by R1 plus R2. So this is 14 2s are, it is nothing but it is 28 divided by 14 plus 2, that is 16. So you can 4 7s are 4 4s are, so 7 by 4 ohms. Okay, 7 by 4 ohms. Now I can write, these are the two terminals. Here we got 7 by 4. Here also we got it as 7 by 4. Here we got it as 7 by 4. These are the terminals A and B. Now we have to find from A to B, means these two are in series, right? So 7 by 4 plus 7 by 4, it will be 7 by 2 ohms. Okay, so I will replace this by another resistor, that is 7 by 2 ohms because they are in series. Now in between these two terminals, the two resistors are connected, that means these two are in parallel. So RAB will be equal to 7 by 2 into 7 by 4, that is divided by 7 by 2 plus 7 by 4. So 7 7s are 49 divided by 8. Here we have 4 7s are 28 plus 7 2s are 14 divided by 8. So this can be written as 42 divided by 8. So 8 8 cancels. It is 49 divided by 48. This is RAB. You can simplify it. you will be getting it as 1.167 ohms. This is your REB. This is the equivalent resistance between the two terminals. Just convert this delta to star, then these two will be in series, okay? Then find out the series value. Then again what happens, to find this equivalent resistance between the two terminals, you can find the delta configuration, means you are going to convert star to delta, and then you see that resistors are in parallel, and then you get the resistors in series. Then again this will be in parallel, okay? From that we can find out the equivalent resistance. So now let us take the second problem. Here also we have to find the equivalent resistance, that is between the two terminals A and B. In this case, see here, this is a point, okay? So these all are B, right? This is B, this is B, this is B. So that means if I consider this as C, this as D, okay? So in between D and B, you have three resistors. That means these are in parallel, right? 54 ohm, 354 ohms are in parallel. So what will be your equivalent resistance for this? That will be 54 divided by 3, right? So that will be equal to, okay, 18 ohms, right? It is 18 ohms. So now I can redraw that. This is 18, this is 6 ohms, this is 6 ohms, this is 6 ohms, and here we have again 18 ohms. So this is your A, this is your B. Now what I will do, see, we can convert this to star, or we can convert this star to delta. Why this is star? Because it is in the form of T connection. This is in the form of pi connection. I had said you that delta we can see in networks in the form of pi, and star we can see it in the form of T in the networks. So this is your star connection, this is your delta connection. Now what I will do is, I will convert this star to delta. Okay, so that means we have equal resistance is 6. So when we are converting from star to delta, it will be multiplied by 3. So 6 3s are 18. We have 18. See, this is our so this is A, this is B, and again we have from this terminal, that is, see, if I consider, we have another resistor 18 ohms. This is 18, this is 18, this is 18, this is 18. Now all are 18, right? So you can see that these two are in parallel, these two are in parallel. So 18 divided by 2, it is 9 ohms. So we can write this as 9 ohms. This also we can write it as 9 ohms. We have to find in between these two, that means these two are in series, right? 9 plus 9, 18. So that will be in series. So we can write this as 18. So we can see these two are in parallel because both are connected to the terminals A and B. So that is 18 divided by 2, 9 ohms. So this will be your equivalent resistor. So that is what you are left with. AB 9 ohms. So 9 ohm will be the answer for this question. Now let us take another one. Here we have to find RCB, then we have to find RAN. Okay, so we have to find the two equivalent resistors in this case. So first we will find RCB, that is between these two terminals B and C, we have to find out the equivalent resistance. So what I can do in that case is I can convert this star which is inside the delta to star. So all are of equal resistances 1 ohm. So in delta it will be multiplied by 3. So inside it will be 3 ohms. So this is 6 and inside you will have 3 ohms. Okay, so you can see this in between C and B you have two resistors connected. So this is the point C, this is the point A, this is the point B. So in between A and B again you have two resistors. So these two resistors, these two and these two are in parallel. So 3 into 6 divided by 3 plus 6. Okay, what is the value? It is 2 ohms, right? So let me consider this as 2 ohms. This is also 2 ohms. That is after simplification 2 ohms. Now we have to find the equivalent resistance between these two terminals. Okay, so from here, if I move from here to this, we can see two resistors are in series. That is 2 plus 2 will be equal to 4 ohms. So in between C and B we have two resistors connected whose value is 4 ohm and another one will be 2 ohm. That means two resistors are in parallel. What will be your RCB? That will be 4 into D2 divided by 4 plus 2, 6. So that is equal to 1.333 ohms. Okay, so that is your answer. Next we have to find out RAN. Okay. What I will do is, I have to find these two. So we can see that this is a delta configuration, right? I will convert this delta configuration 6 ohm. Here we have 1 ohm. Here we have 1 ohm. So this I will convert it into star. I'll keep this as it is. I will convert this delta now. Okay, what will be the value of this? See, you know it is adjacent branches 1 into 1 divided by sum of all the resistances, that is 8. Okay, here it is 1 into 6 divided by 8. Here it will be, this is 1 ohm, sorry. Now this is 1 into 6 divided by 8. So this is 1 by 8, this is 6 by 8, this is 6 by 8. Now I can redraw this. So A to N it is constant, that is having the resistance 1 ohm. Now I have converted this delta to star. So I will write this star here now. So this is the value N, this is C and this is B. So this is C, this is B and this is N, right? So now in between B and C, we do not have anything because we have already converted it into star. From A to C, we have one resistor 6 ohm and here also we have another resistor 6 ohm. This is 1 ohm. So this is 1 by 8, this is 6 by 8, this is 6 by 8. Okay, so this is what we can consider. Now we can see these two are in series, right? These two are in series. I'll consider this some point as E or S. I will consider it as star point. Yes. Okay, from A to S, we have these two in series and these two in series. So 6 plus 6 by 8. So this can be actually simplified. So 6 4s are 24 plus 3, 27. So these two are in parallel. That means the equivalent will be 27 divided by 8. So we can redraw this now. It is in between the terminals A and N. This is 27 divided by 8. This is 1 divided by 8. This is 1 ohm. So in between this we have to find out the equivalent resistance. That means these two are in series. So 27 divided by 8 plus 1 divided by 8, that will be equal to 28 divided by 8. So 214 or 4 7s are 4 2s are 7 divided by 2. Then we can see we have two resistors in between A and N. This is 1 ohm. This is 7 by 2 ohms. So it is in parallel. 7 by 2 into 1, 7 by 2 plus 1. So this will be 7 by 2. This will be 9 by 2. So that will be equal to 7 by 9 ohms, whose also value can be written as 0.77 ohms. This will be your RA.